Hello everybody, and welcome to our video on transformations of functions. So here we're going to consider the following transformations of functions: vertical shifts, horizontal shifts, reflections about the y-axis, reflections about the x-axis, vertical stretch and compression, and horizontal stretch and compression. So one thing that I want to emphasize here is that transformations always act the same on all functions. So what we're going to do is just examine a simple function that's defined by a table of values and look at how it transforms those values, and then generalize this to more types of functions after that. So let's start by looking at vertical shifts. So we've got some x values here, 1, 2, 3, and 4. And so our function f, which we're going to denote with blue, has the output values 3, -1, 2, and 4, respectively for each input. So when x is 1, we get 3. When x is 2, we get -1. And then 3, 2, and 4, 4. All right, so what we're going to do is look at this transformation in green. So our new function g is going to be defined by f of x plus 2. So in other words, when I plug in these same x values, g of 1 will be f of 1 plus 2. Well, f of 1 is 3, plus 2 is 5. So this is going to give me 5. And then g of 2 here is f of 2 plus 2. So we're taking the y value from here and adding 2 to it. That gives us 1. Okay, g of 3 is f of 3 plus 2. So that's 2 plus 2, which is 4. And g of 4 is f of 4 plus 2. That's 4 plus 2, which is 6. Okay, so let's just take a look. What happened to each point? So each point moved up by 2. Now, of course, we're laying this out really precisely, but it should be kind of obvious that this is happening, because what we're saying here by this transformation is that you're taking the y value from our previous function and adding 2 to that y value. So of course your y value goes up by 2. Now in general, we describe y equals f of x plus d as a vertical shift of f by d. If d is positive, the graph shifts up, and if d is negative, the graph shifts down. All right, so let's look at horizontal shifts. So these work a little bit differently. So here, the action is, instead of occurring outside of the function, so adding to the outside of the function after y has been calculated, instead we add or subtract to the x value inside the function. So here, x is 1, 2, 3, and 4, and we've got the same outputs, 3, -1, 2, and 4. So let's plot those. And again, we'll plot that in blue. Okay. Now, what we're going to do is actually look at different x values here, because keep in mind, what's changing here is the input of the function. So we need to look at how the behavior affects the input, the x value. So if I was to instead look at x is 4, g of 4 is f of 4 minus 3, which is f of 1. So in other words, you get the same y value that you got over here, which is 3. So when x is 4, y is 3. Actually, I'm going to switch my second function to purple here, I think, or orange. Let's do orange. I think that's a little bit more distinct. Okay, now let's take a look at when x is 5. So g of 5 gives us f of 5 minus 3, which is f of 2, which is -1. All right, g of 6 is f of 6 minus 3, which is f of 3, which equals 2. And g of 7 is f of 7 minus 3, which is f of 4, which we know was 4. All right, so what happened here? Well, each point on our graph shifted to the right by 3. So each graph shifts to the right by 3. So how we can think about that is, in order to get the same output value, our input had to be 3 larger to compensate for the fact that we were subtracting 3. Now, in general, my recommendation for solving horizontal shifts is to take whatever your input for your function is, set it equal to 0, and solve it. So this would be a shift right by 3. Now, this is kind of important thing to distinguish from, because if we had something in front of this x, like if it was 2x minus 3, the shift would not be 3. And by solving the equation like this, it ensures that we always get the correct shift, regardless of, if x is being multiplied by anything. We can avoid having any confusion there. But in the simple case where it's just x minus a number, you shift right. So when we write this expression, y equals f of x minus c, this is a horizontal shift of f by c. And if c is positive, then the graph shifts right, and if c is negative, then the graph shifts left. So notice, in this case, the negative is built into the formula here. So when we say c is negative, it would be negative a negative number, so the result would be something positive. Hopefully that's clear. So in this example, c is 3. And if I had, say, f of x plus 2, c is actually negative 2. But again, we can kind of avoid having any confusion regarding the value of c in terms of our horizontal shift by just taking the input of our function, setting it equal to 0, and solving it. You'll always get the shift right that way. Okay, so let's take a look at an example here. We're going to graph y equals x squared. Then we're going to graph y equals x minus 1 squared and y equals x squared plus 1 on the same plane. So first, let's graph y equals x squared. This is a nice basic graph. We've looked at this a few times already. So I'm just going to color code which graph is which by underlining it with the color. Okay, so y equals x minus 1 squared. Well, it looks like x squared, but my input was replaced with x minus 1. So if I set this equal to 0 and solve it, this tells me I shift right 1. So I'm just going to take every point and move every point to the right by 1, just like I did for my table graph. It's the same thing. You just take every point on your graph, move it to the right by 1. Now here, we're taking f of x and we're adding 1 to it. So this is a shift up by 1. So you start with your original graph in blue and just shift every point up 1. It's not a perfect picture, but hopefully it's clear enough. All right, that's the basic idea there. So let's move on to reflections. So first of all, reflections about the y-axis. So we'll start with, again, the same set of points here. So this is when x is 1, we get 3, 2, negative 1, 3, 2, and 4, 4. Okay, now, what we're going to look at is the function g of x equals f of negative x. So, we might suspect correctly that that means we need to look at the opposite x values. So when x is -1, g of -1 is f of -1, which is equal to f of 1, which we already know is 3. So for x equal to -1, y equals 3. And then when x is -2, g of -2 is going to give me f of 2, which is -1. And then when g is equal to, or x is equal to -3, g of -3 is equal to f of 3, which is 2. And g of -4 equals 4. Okay, so what do we see here? Well, we see that all of our points on our graph are flipping from positive x values to negative x values. So it does exactly what we said, which is it reflects these points about the y-axis, gives you a mirror image over the y-axis. So in general, we describe y equals f of -x as a, quote, reflection of f over the y-axis. Okay, now let's look at reflections about the x-axis. So here, again, same starting points. 1, 3, 2, -1, 3, 2, and 4, 4. Okay, and now what are we going to look at? Well, in this case, the action, the negative value, is being applied to the outside of f of x. So here, what was being changed was the input, so we adjusted the input to compensate. Here, what's being changed is the output of the function, so we're going to keep the input the same and see what happens to the output. So g of 1 is equal to -f of 1, which is -3. G of 2 is equal to -f of 2, that's -1, which becomes +1. G of 3 is -f of 3, which gives us -2. And g of 4 is -f of 4, which is -4. All right, so what happened here? Well, each of our values just flipped over the x-axis, which should make sense because we were just taking the previous y value and making that y value negative. So we end up on the opposite side of the x-axis. So in general, we describe y equals -f of x as a, quote, reflection of f over the x-axis. Okay, so let's take a look at a couple quick examples of this. First one here, graph y equals x cubed. And y equals parentheses -x cubed on the same plane. So in blue, we'll draw y equals x cubed. Looks roughly like this. So if I want -x cubed, what happens is all my points are going to get flipped. The x values are going to become negative, so they're going to get flipped this way and this way, right? So what does my graph look like? Roughly like this. Because that's a reflection over the y-axis. Okay, so example 3, graph y equals x squared and y equals -x squared on the same plane. So here, this negative is being applied outside of the function. So we've already evaluated f of x, and we're making the whole thing negative. So this is a reflection over the x-axis. Okay, so y equals x squared. So if I reflect it over the x-axis, of course, the y equal to 0 doesn't change, but all my other values, the y values become negative, and so it looks roughly like this. All right, moving on to horizontal stretch and compression. All right, x equals 1, 2, 3, and 4, and y equals 3, negative 1, 2, and 4. So that's our usual example here. Okay, so what happens to this function? Oh, wait, my graph is messed up. Drew my points in the wrong spot. There we go. Okay, so now we're looking at the function g of x equals f of 2 times x. So here, whatever x value we have, we plug into this function g, we double it, and then evaluate it with f. So, as you might guess, we have to compensate for the value of x by cutting the value of x in half each time. So, here, when x is 1/2, we get g of 1/2, which is equal to f of 2 times 1/2, which is f of 1, which is 3. So, we get 1/2, 3. Now, when x is 1, g of 1 is f of 2 times 1, which is f of 2, which is negative 1. Now, when x is 3/2, we get f of 2 times 3/2, which is f of 3, which is 2. And here, when x is 2, we get f of 2 times 2, which is f of 4, which is 4. So what you should see here is that the behavior of our function sort of shrunk to where the same behavior is occurring in half the space that it was occurring in before, right? So in general, if the absolute value of this number is greater than 1, we say that f of b times x experiences a horizontal compression by a factor of b. And if the absolute value of b is less than 1, we say that it experiences a horizontal stretch by a factor of b. Okay, let's take a look at the vertical stretch and compression. All right, same starting point here. 1, and But now, the function we're looking at, g of x equals 2 times f of x. So, f of x is being evaluated first, and then multiplying the result by 2. So, g of 1 equals 2 times f of 1, which is 2 times 3, which is 6. So, this is 6. G of 2 is 2 times f of 2, which is 2 times negative 1, which is negative 2. G of 3 is 2 times f of 3. That's 2 times 2, which is 4. And g of 4 is 2 times f of 4, which is 8. So here, what do we see? Well, our values for the vertical distance between our values has been doubled, right? The amount of space between our largest and smallest values is doubled. So our function is being stretched out. So we call this, if the absolute value of a is greater than or equal to 1, we say that a times f of x experiences a vertical stretch. And if the absolute value of a is less than 1, we say that a times f of x experiences a vertical compression. So again, these conditions look about opposite to the conditions for horizontal stretch. Just like when we talked about the shifts seemed to be the opposite thing happening between vertical and horizontal shifts, like +2 is a shift up, -3 is a shift right. This is a similar thing here because this is all about the order of operations. That's what you have to keep in mind here. Because we're multiplying by 2 to our input first, we have to compensate the input to end up with the same output values. Here, we're multiplying by 2 after the function has been evaluated. So instead, what's being compensated, what's being changed is the output values directly. And that reverse of the order of operations in what's happening here is also causing us to seem to get an opposite effect, even though it's not really opposite, it's just because of the order of operations. Okay, so example 4 here, graph y equals x squared, y equals 2x all squared, and y equals x over 2 all squared on the same plane. So generally with most functions we graph, there will be a couple like basic points that we'll start with. So for x squared, right, it's always 0, 1, and 2 for the x values, and then it's an even function, so you just mirror them. So if I'm going to graph these transformations, I'm always going to start by just looking at those points and transforming them appropriately. So here we've got 2 times x. So this should be a compression by a factor of 2. In other words, everything should be pulled in the x direction to 1/2 of the distance it was before. And here, this should be a stretch by a factor of 2. I could say by a factor of 1/2. Depends on how you want to phrase that, but I'm not too picky about that in particular. So here we start with our original points, and they should each double their distance from the y-axis. So this should look roughly like this. Okay, y equals x squared again. Now we'll look at y equals 2x squared, so this should be a stretch by 2. So everything should be getting stretched upwards, double its distance from the x-axis. Oh, those points are not correct. Let's try that again. I forgot how to count. Please forgive me. That should be there and there. And here, this should be compression by 1/2. So everything should get shrunk down to 1/2 its distance from the x-axis. Okay, so now to tie this all together, we got to think about combining multiple transformations. So this is kind of a tricky topic. I have a very particular way that I think this should be approached, but there are multiple approaches to it that you can see. So the order that you carry out your transformation can actually change how you need to interpret your transformations. So that's the key thing to understand here. When you get a correct method, you should stick to it for consistency. Otherwise, you may make mistakes in interpreting your transformations if you change the order that you interpret them in. So I consider the following approach to be the most consistent because it's based on the order of operations, PEMDAS, parentheses, exponents, multiplication and division, addition and subtraction. So if we have a function like this looks very complicated, y equals plus or minus a times f of plus or minus bx minus s plus h, where a and b are positive, we would graph our transformations in the following order. So we go from f of x to f of bx because we're inside the parentheses, so we have to deal with everything inside parentheses first. And this is multiplication by x. So that's the first thing that's going to happen inside this parentheses is the multiplication by x. And then I deal with this plus or minus. That's multiplication again, but it results in a reflection, but it's really just multiplying by plus or minus 1. So I deal with the b first, if assuming b is positive, then the plus or minus, the reflection about the y-axis. Then the minus s here, which is going to be our horizontal shift, right? Because then we get to addition and subtraction, right? So we dealt with the multiplication, division, and addition and subtraction. Now we're done with all of the parentheses, right? So these first steps are all inside the parentheses. So we were doing parentheses first, and inside the parentheses, we use the order of operations to deal with these transformations first. Then outside of the parentheses in here, we've got multiplication again, a times the function. And then multiplication again, plus or minus 1 times a times the function. That's our reflection over the x-axis. And then addition and subtraction at the end, right? So this approach is just the order of operations carried out on your transformations. One thing I want to point out, though, is that to make sure you're not making mistakes on interpreting your transformations, your horizontal shift should always be determined by taking your input, that's this thing, and setting it equal to 0 to solve for x, or first factoring your expression into this form, and then your horizontal shift would be given by c. But personally, I think it's simpler to just consistently take this, set it equal to 0. I find that students make the least mistakes if they take this approach. All right, so first we're going to describe the transformations from the parent function and then graph it. So the parent function is the most basic version of the function that you can find. So here we look at this x plus 1 cubed, then we've got a negative in front plus 2. So the parent function for this we'll call p of x is just x cubed. So let's take a look at our transformations. So the first thing I deal with is what's inside the parentheses, and here we've just got x plus 1. So we transformed this to x plus 1 cubed, and x plus 1 equal to 0 solves to x equals negative 1. So this is a shift left 1. Okay, next we deal with the multiplication outside of the parentheses. So that's going to give us, that's negative f of x. So that's a reflection over the x-axis. Now we've got the plus 2 at the end. So this is just a shift up 2. So now we're just going to graph each of these shifts, and I'm going to kind of sketch this quickly. I'm not going to be super precise. We've graphed x cubed enough times here, I think. It looks something like this. Okay, so we'll start by shifting it left by 1. Again, all you're going to do is take every point on your graph and move it over 1. So I just took each point and shifted them over by 1. Oops, that one's not correct. Let's try that again. There we go. Now we need to reflect over the x-axis. Now, here's the thing to keep in mind here, is that the transformations you're doing now are transformations done one at a time on just the previous step. The first transformation we did shifted just the x cubed. Now we're reflecting the entire x plus 1 cubed function that we just drew. So we deal with that reflection for the whole thing. Right, after we deal with the reflection on this graph specifically. Okay, again, this is just a rough graph, so forgive me for being a little bit quick about it, but just take every point and move it up 2. Hopefully that's at least a good enough of a picture to give you the idea of what's going on here. Okay, so let's go ahead and move on and deal with one more example. So again, first describe the transformations from the parent function, then graph f of x. So we look here, we've got the absolute value of this thing. So, yeah, what are we going to do here? Well, we're going to start with our parent function, which is just the absolute value of x. Now, the first transformation I'm going to look at is, of course, the multiplication by -1 of x. So this transforms to y equals the absolute value of -x, and that gives us a reflection over the y-axis. Now we're adding something to this whole thing. And this is a perfect example of what I warned about before, which is that if you've got something other than +1 in front of your x, it can change how you interpret your shift here. So this is a shift, but if we solve this, oh, not sure what happened there. Let me get back to that page. There we go. If we solve 3 minus x equal to 0, that gives us x equals 3. So that tells us this is a shift right by 3. So you might be tempted to think, oh, it's the opposite of 3, so left 3. But that's not correct. That's why I always insist that you set this equal to 0 and solve it to see what x needs to compensate for to give you the same original input values. So it's best to just set this equal to 0 and solve it, so you don't make mistakes when you have a weird case like this one. Okay, what's next? Well, now we've got a 1/2 in front. So that's a vertical compression by 1/2. And then we're multiplying that by -1. So that's a reflection over the x-axis. Yes, over the x-axis. And then finally, -1/2. The absolute value of 3 minus x minus 1. So this is down 1. Okay, so let's just go through and graph each of these things one at a time. So we've seen earlier that the absolute value looks like this. So one step at a time. Now we reflect over the y-axis. So we're going to take all of our points and flip them around. And that's an interesting thing here, because if I do that, what happens? Well, the points switch places, but because this function is even, it actually doesn't change the graph. So that's a key thing to understand here. All right, because what do we know about the absolute value of x? It's the same thing as the absolute value of negative x, right? So just like the function is the same thing if you put a negative inside first, the graph is the same when you do your reflection over the y-axis. This is a fact for all even functions. Any even function, if you reflect it over the y-axis, just gives you the same picture. So, what's next? Go right by 3. So just take each point and shift it over by 3. Then we've got a vertical compression by 1/2. So that just means our y values are going to shrink down half the distance from where they were before. Of course, when y is 0, that point doesn't change. But the other ones shrink down here from 1 to 1/2. So the graph kind of flattens out a little bit. What's next? So we've done our vertical compression by 1/2. So now we have a reflection over the x-axis. So now we just take our graph and we flip it down here. And finally, we want to shift down by 1. So we'll just take every point . Move them down 1, and we're done. All right, so that's it for transformations of functions. Now you're going to learn about a whole lot of other functions in this course that are going to have a whole lot of transformations done to them. So the key thing to understand is that all of these transformations always work the same way, right? The way you interpret these is always the same. And so if you understand this concept in general for a general function f of x, then you'll be able to apply it to any future functions you learn about. All right, well, I hope that was helpful. Thank you for watching.